Welcome to this part of the Red Door Analytics online course, Survival Analysis, an introduction to concepts, methods, and software. In this section, we'll be talking about hazard and cumulative hazard. And this is an introduction prior to us talking about modelling, but a little bit about survival analysis models before we talk about the hazard function. Standard regression models, for example, logistic regression, do not account for censoring and differ in time at risk. And that's one of the reasons why we have specific survival analysis models. In this course, we'll be covering some of the most common ones: the exponential model, the Weibull model, the Poisson, and the Cox proportional hazards model. These will be presented in one of our subsequent sessions. But since these commonly used models model the hazard function, we will focus on modeling the hazard. Do note, though, that there are models which model different transformations. For example, Laplace regression focuses on modeling the survival function. And it's also common to model the cumulative hazard function when using flexible parametric survival models. We're not going to cover these models in this course, but there are some references here. But the thing to note is that there are mathematical relationships between the hazard and the survival function. But what is the hazard function? Well, here we define it as lambda t, so it's a function of time t, and it's the instantaneous rate of the event of interest. And it can be written in this way, where we have lowercase t as a time or a time scale, and capital T is the event time. The thing to note is that this is related to the survival function in this way, where we have that the hazard function is equal to the negative of the derivative of the log of the survival function. So we can look at the hazard function and get the survival function out, and vice versa. So we may be interested in presenting the hazard function graphically. Here we have an example of a hazard function. This is just an example. It doesn't have to look like this at all. The shapes can vary a lot. But we can see that we have on the y-axis the hazard rate per person year, and we have time since diagnosis on our x-axis, our time scale. Note that the hazard function is always above 0. And in this specific example, we can see that from the time of diagnosis, or from time 0 here, the hazard rate is increasing until around about 2 years, at which point it starts to decrease again. And then around 3 years, it starts to flatten out. There's also something called the cumulative hazard function that's often used and presented in survival analysis. Here we denote it capital lambda t. This presents the cumulative risk of the event from time 0 to time t, and it's just the integral of this hazard function. So one example of what it might look like is presented here, where we have the y-axis representing the cumulative hazard rate. And again, on the x-axis, we have the time scale, time since diagnosis. So this is just the integral of the previous curve that I presented you. And you can see that this is an increasing function over time, and it starts at 0. So here I present the survival, the hazard, and the cumulative hazard side by side. These are all interrelated functions, and you should see some relationships between those. If we think about the survival function on the left-hand side of the slide, we should see that where the survival function is the steepest, we see that the hazard function is the highest. And this is the relationship that we have. And again, we discussed the fact that the cumulative hazard function is the integral of the hazard function. So the most important take-home message from this is that these are different measures in survival analysis, and they are all interrelated. Here's some further reading if you'd like to do some, and I'll see you in the next section of the course.